Welcome back. In this video, we're going to begin learning about reaction enthalpy. And by begin, I mean actually we're going to be reviewing some things that we've already seen earlier in the semester, but now we're going to look at them in a new light. So what we're going to do is we're going to differentiate between a normal balanced chemical equation and what we call a thermochemical equation. We will discuss enthalpy, enthalpy changes, how to identify reactions as endothermic or exothermic, and drawing energy diagrams for enthalpy changes. So enthalpy is the amount of heat that's transferred when we do a reaction at constant pressure. And we've examined changes in enthalpy before for physical changes. We've looked at freezing and melting, and we've looked at vaporization and condensation. We've also talked about sublimation and deposition. Enthalpy changes are also associated with chemical changes. And it's easy for this to make sense if you think of it as we're just talking about the energy that's transferred between substances during a reaction, whether that's a physical reaction or a chemical reaction. So there are heats of reaction or enthalpies of reaction. This is a very generic term describing the enthalpy change that's associated with a chemical reaction. We also have the heat of formation or enthalpy of formation. This is a specific type of chemical reaction. This is a chemical reaction that involves forming a compound from elements only. And we'll talk more about heats of formation in a later video. So let's talk about some of the characteristics of enthalpy. We can describe the change in enthalpy as the initial enthalpy state minus the final, the final enthalpy state minus the initial. And for a given reaction, this would be the enthalpy of the products minus the enthalpy of the reactants. If the enthalpy is greater than 0, we say that this is an endothermic reaction. And if it's less than 0, then it's exothermic. Enthalpy is also an extensive property. What this means is that the amount of enthalpy given off or absorbed is going to depend on the amount of material used or produced. And this should make sense if you think of it in terms of a chemical reaction. If you have 1 kilogram of reactants that are forming your products, and that gives off a certain amount of energy. If you double the amount of reactants, then that should double the amount of energy. Also, the change in enthalpy for a reaction, if you were to reverse the chemical reaction, it reverses the sign of the enthalpy, but the magnitude stays the same. Finally, the enthalpy of a reaction is going to depend on the states of matter, whether our substances are solid, liquid, or gas. Let's look at each of these with an example. So let's say that we're taking and doing a combustion reaction with methane to produce carbon dioxide and water. The enthalpy of reaction is negative 802.3 kilojoules. What this means is that if we were to have 1 mole of methane reacting with 2 moles of oxygen, it would produce 1 mole of carbon dioxide, 2 moles of water, as well as 802.3 kilojoules of energy. To illustrate how enthalpy is an extensive property, if we were to double the amount of reactants, we would double the amount of products, including our enthalpy. For observing how, if we were to reverse the reaction, that would reverse the enthalpy, because the combustion reaction gives off energy, if we were to somehow be able to take and recombine the carbon dioxide and the water, that's going to require an input of energy equal to the same amount of energy that would have been released from the combustion reaction. Then finally, the state of matter that our substances are in will affect the enthalpies. So if we compare, we have, in this case, the initial reaction had all states of matter of gases. However, when we write it this way, our water is instead a liquid. And what we see is that the energy released is actually larger than in the case of if water was a gas. Now, how can we imagine this? How can this make sense to us? Well, remember that if we look at the energy of a gas versus a liquid versus a solid, a substance that is gaseous has higher total energy than that same substance if it were a liquid. And in order to change from a gas to a liquid, for it to condense, that must release energy into the surroundings. Therefore, if we were to take our first reaction and change to get this final reaction, we're taking a gaseous water molecule and converting it to liquid, which must then give off energy. Therefore, the total energy of the reaction is going to be more exothermic than in the original. So thermochemistry is the study of energy changes involved in chemical processes. Chemical energy is a type of potential energy that's associated with bonding. So if we were to take hydrogen gas and oxygen gas, combine them to form water, we can look at this as a rearrangement of the hydrogen and oxygen atoms. If we were to look at the energies or the enthalpies of the reactants versus products, we can see that the reactants are higher in energy than our products. Therefore, our enthalpy of reaction is going to be negative, or an exothermic reaction. Heat's going to be lost to our surroundings. For this particular reaction, it gives off 483.6 kilojoules per mole. A thermochemical equation is simply a balanced chemical equation which incorporates that enthalpy change. So if we were to initially ignore any energy associated with a chemical reaction, that's just a regular balanced chemical equation. Once we consider for the energy change involved, we now call that a thermochemical equation. All right, here are a couple practice problems for us to think about what's going on here. So the temperature of a hydrogen peroxide solution increases as the hydrogen peroxide decomposes into water and oxygen. Based on this information, which energy level best describes the enthalpy level of the products of this reaction? How do we think about this? We know that for exothermic processes, these are indicated by an increase of the temperature as indicated by the surroundings. Our thermometer is part of the surroundings, and it measures an increase of temperature for this reaction. In the prompt, it says that the temperature of the solution increases as the decomposition occurs. Because the thermometer is part of the surroundings and the thermometer's temperature went up, the thermometer absorbed in energy from our system, and therefore the reaction must be exothermic. Since it's exothermic, that means our products must be lower in energy than our reactants. And therefore, the answer to the products would be written down somewhere down here, as opposed to with A or B. Here's one more problem. This is a more quantitative problem. In this question, we want to know how much heat would be released by the reaction of 12 grams of methane reacting with 22 grams of oxygen to form liquid water and carbon dioxide. So to evaluate this, we want to, what are we trying to determine? We want to know how much total heat is released for a given amount of reactants. We know that if we had 1 mole of methane and 2 moles of oxygen, then we would give off 890.3 kilojoules. But we need to consider how many moles do we actually have. So first, we want to find the heat given off from the reaction. So we use the information that we're given. We're given the mass of methane and the mass of oxygen. we need to find out how many moles of each of these there are, and then determine if there's a limiting reactant. So we can use the molar mass of methane and the molar mass of oxygen to find the number of moles of each of them. For methane, we have 3/4 of a mole, and for oxygen, we have 0.688 moles. Now, we need to find out the amount of product that's produced when our reactants are consumed. So for methane, we have 3/4 of a mole of methane, and the ratio is given on a per reaction basis. And if you look at the reaction, it's per 1 mole of methane. That's where this ratio comes from. So if we were to use all of our methane, it would give off 668 kilojoules. Now, to find out how much we would produce if all of the oxygen was consumed, we have 0.688 moles of oxygen, and the ratio here is 890.3 kilojoules per 2 moles of oxygen. That would produce 306 kilojoules. So in the same way that we've evaluated before, what is our limiting reactant, we can evaluate here that oxygen is our limiting reactant because it would produce less heat. In other words, we can think of heat as another product in this case. Or if it were endothermic, we could think of heat as a reactant. Since oxygen is our limiting reactant, we've already then determined that we can produce 306 kilojoules of heat. And so we release that much heat. Notice in our answers that the value here is not negative. And the reason for that is because we've modified it by saying it's the energy released. If we were to ask what would be the heat change, then in that case, our final answer should include the negative sign. That's it for this video. Thanks for watching. Have a wonderful day.